When we observe what we call fire, we have this combustion reaction going on, and then we see these flames. What we're really observing are the three forms of thermal energy transfer. We're observing conduction, convection, and thermal radiation all at the same time. So it is thermal radiation. And I could say thermal conduction, thermal convection, and thermal radiation. The word thermal is just relating to things dealing with temperature. So what is the conduction going on?
Physical Science 5.2, Conduction, Convection, and Radiation. What are those three things? And how do thermal conductors differ from thermal insulators? How are thermal insulators used to control the transfer of thermal energy? In last section, we actually touched on that with the video, but we're going to go a little bit deeper this time. Conduction, convection, and radiation, they all transfer energy. So the question is, how does conduction do that? Well, it's the transfer of thermal energy by collisions between the particles that make up matter. Conduction occurs because particles that make up matter are in constant motion. So when this metal spoon goes into this heat, into this other piece of matter, it's going to conduct its energy.
The fuel for our fire. So down here, the fuel for our fire, we have our classic combustion reaction, and I encourage you to watch the video on that in our chemistry playlist or our chemistry section if you're interested in it. But
This is Khan Academy, by the way.
Taking carbon molecules and their bonds, and then in the presence of oxygen and some heat, you have a combustion reaction producing carbon dioxide and producing water, and even more energy than you put into it. So it's producing a lot of energy. And that energy is going to excite the molecules that are around it. So you have these molecules that end up getting a lot of kinetic energy. And remember, temperature is proportional to average kinetic energy. And so the ones that just combusted, or the molecules right near the reaction, or maybe the ones that were part of the reaction, they're going to have this really high average kinetic energy, because all of this energy was released from that combustion reaction. And then they're going to bump into other molecules that might not have quite as high kinetic energy, but then they're going to transfer that kinetic energy through these collisions. And we have a whole video on thermal conduction, but that's what's happening. Things with higher kinetic energy are bumping into things with lower kinetic energy and transferring some of that kinetic energy, and they're transferring some of that momentum. So that is definitely happening when we look at a fire like this, that neighboring molecules are bumping into other molecules and transferring energy.
Unlike solids, liquids and gases are fluids that flow. In fluids, convection can transfer thermal energy, and we have been talking about that since, the first month of school. Convection is the transfer of thermal energy in a fluid by the movement of warmer and cooler fluid. When conduction occurs, more energetic particles collide with less energetic particles and transfer thermal energy. When convection occurs, more energetic particles move from one place to another. Heat rises because it becomes less dense, and as it gets cool, it sinks because it becomes more dense, just like the lava lamp.
Now convection, this is around the idea that hot air is less dense. And so if we have a bunch of air particles here, so let's say this is the cool air up here, and it makes sense why cool air is going to be more dense than hot air. Because hot air, these particles have a much higher kinetic energy. And so they're going to bump into each other, and they're going to push each other much further away and get more separation from each other because of that high average kinetic energy. But because the hot area is less dense, this area right over here is less dense than the white area. These might all be the same molecule. I just made them in different colors to show the less dense area and the more dense area. It is going to rise. It is going to rise, or you could even think of it as the more dense area. The more dense area is going to fall around it. Is going to fall around it or try to go under it because it is more dense, and then the less dense area is going to rise. And by doing that, you have the hotter molecules are moving upwards, and then the cold molecules can go down to maybe the source of heat, the source of energy right over here, to get heated up more. So this right over here, so hot air rises. Let me write this. The hot air rises. And one way to think about it, makes room for the cooled air to come down and then get heated up again. And that's what's going on in the fire here. You see the combustion reaction? Combustion reaction occurs right over there. Let me do this in a different color. Combustion reaction is occurring in the fuel. The super hot air, it's going to rise. And that's why it looks like these flames are kind of, they're moving upwards. They're kind of flickering upwards. And you'll also see, and actually we're going to talk about this in thermal radiation, is that they also change color as they move upwards. But this whole idea of fire moving upwards and the hot air, if you put your hand up here, it's going to be much hotter than if you were to put your hand, say, right here. Even though in theory this is closer to the flame than
that comes in real handy when you want to roast a marshmallow. Just saying.
Up here, and that's because the hot air is rising and it's making room for cold air, or cooler air, I guess I could say, come down here and get heated up again, and then it would rise up again. And so this convection, this idea of the hot air rising or the cold air falling, this is another form of heat transfer.
So the last form is radiation, and it's the transfer of energy by electromagnetic waves. Those waves are like light and microwaves. These waves travel through space, even when matter is not present. It can travel through a vacuum. Energy that is transferred by radiation is often called radiant energy. When you stand near a fire, radiation transfers energy from the fire and increases the thermal energy of your body. Same can be said for the sun.
When we're looking at fire, is thermal radiation. And this is all around the idea that if you have charged particles being accelerated, they're going to release electromagnetic radiation. And so you might say, wait, charged particles, where are those being accelerated here? Well, we have these molecules that are constantly being accelerated as they bump into each other. One's going to transfer kinetic energy from, let's say this one bumps into that, it's going to accelerate that in a different direction. And even this one might go in another direction, and acceleration is a change in velocity. So it could be the magnitude of velocity or your direction of velocity. So as they're colliding, you have all of these acceleration of charged particles. So let me write this down. You have acceleration of charged particles, and then that releases electromagnetic radiation. I know what you're thinking. Wait, hold on a second, Sal. I can buy that we have molecules that are being accelerated, but where are you getting this charged particles business? Well, we have to remember these molecules are made up of atoms, and atoms are made up of charged particles. They're made up of protons and electrons. And so as you accelerate these, and the more that you accelerate these, the more radiation you are going to release. And you might say, wait, okay, you said I'm observing that in fire. Where am I observing radiation? Well, just the very fact that you can see the fire, the light emitted from the fire, that is electromagnetic radiation. It's just the electromagnetic radiation in the wavelengths that your eye considers to be visible light, or that your eye considers to be light. Even the particles up here that are still quite hot, they are also emitting electromagnetic radiation because they're all bumping into each other, and their electrons and their protons are all getting accelerated in different ways. They're also releasing electromagnetic radiation, but it is at a slower wavelength than your eye is capable of perceiving as light. If you had an infrared camera, you would see the flames being much larger. You would see them go all the way up here. And if you were to look at the flame closely, you would see down here, right where the combustion reaction is happening, the flame looks blue. And that's because the blue light is higher energy light. And that's because the particles are being accelerated more down here. And then it goes from blue to kind of white, to a yellow, to a red, or to an orange, to a red.
Which you learned about in both chemistry and pre-chemistry.
And then to your regular eyes, it disappears. But everything that has some temperature is releasing electromagnetic radiation. And you're like, okay, well, that's all fine. I can see it. But how is that a form of energy transfer? Well, if you've ever sat next to a flame, you will feel the heat. In fact, even if the air between you and the flame is cold, you would still feel like you're getting warm.
So you might not realize it, but you probably do a number of things every day to control thermal energy transfers between your body and your body's surroundings. For example, when it's cold outside, you put on a coat, right? When you reach into an oven to pull out a hot dish, what do? Just stick your hand in there? No, you get a cloth, an oven mitt, something to protect your skin from that hot scalding metal.